All right, good morning, everyone. This is Joseph Dufresne with SAMSON Controls. This morning, we're going to do a presentation on our positioner product overview. So just FYI, in case you didn't notice, this webinar is being recorded, so I just wanted to disclose that to you. So I'll start off with a little introduction about myself and let the other presenter, Rick Burke, also do a little introduction. So like I said, my name is Joseph Dufresne. I've been with SAMSON for 15 years. In my roles, I've done everything from inside sales, outside sales, R&D. My current role is product manager. One of my key products is the Positioner product portfolio. I have engineering degrees in electrical engineering focused on telecommunications and control theory. So that really lends itself to the product that I'm going to be talking about today with our positioners. So I'll go ahead and let Rick Burke do a quick introduction on himself, and then we'll get started.
Yeah, so I've been with SAMSON. I'm a regional sales manager in the Southeast Texas area, and had this position for 11 years with SAMSON Controls. And I've been in various roles at other manufacturers for valves and various control products for 34 years. So I've been doing this a long time, and glad to see everybody here.
All right, so the goal of this presentation is to provide kind of a brief overview of the SAMSON Positioner product portfolio and offer some insights into how our products can help resolve end users' application needs, as well as their process requirements. So we'll get started and start off with some definitions and clarifications. So we're going to start with kind of the basics of control. So an element that can be used to control a process control loop is what's called an Idp converter or a transducer. Now, an Idp converter sends an open or close request or a modulating request to the valve, but it cannot confirm the position. So in this control loop example that I have here, we've got our media or medium M that's running through our final control element, the control valve. There's some disturbance that could occur, wanted or unwanted, that impacts our process. We take that result, and that's called our controlled process variable. We take a measurement of that process variable, and we send that to a controller. We compare that to our desired set point. That creates an error or an offset that then goes into make a request to the Idp converter, and it sends a signal to the actuator to move with the output of the Idp represented here by the term Y. So if we look at how an Idp functions, you can think of it as like a functional table, lookup table. So if we give the Idp transducer an input current that ranges from 4 to 20 milliamps, and we expect the output to be 3 to 15, then it would be just a straight lookup. So 4 milliamps would equal 3 psi, 12 milliamps would equal 50% of the output, or 9 psi, and 20 milliamps would equal the 15 maximum output of that Idp. So if there is a difference in the pressure required to move the valve or a change in the frictional profile of that valve, the transducer cannot correct this offset. So the process control loop will constantly trying to remove that deviation and try to achieve the controlled position that you've desired through the controller. A little bit different with the positioner. So a positioner is a control, a valve controller that ensures the valve is at the correct position by adjusting actuator force, by comparing the controlled signal or reference variable with the actual movement of the valve, the stem position. So it is a feedback controller. So once again, we have the process going through control valve. We have some type of disturbance that was introduced to the process. We measure our controlled process variable that we're trying to control. We compare that to a set point value that creates a correction or error factor, which then results in the output that goes to the positioner. Now, if we look at how a positioner works, it is also a closed loop control loop inside of it. So here, if you start with the signal W, which would be our set point, we go through an A to D, so an analog to digital converter. It then goes to a microcontroller to make the control adjustments, take in that input, gets changed back to an analog signal that goes to a controller. The controller compares the travel or current position of the valve and outputs a change signal that then goes to an Idp. So here we're changing that current-based output to a pneumatic output, and then that goes through a volume booster that then moves the control valve. The movement of the control valve is measured. So here we're starting with the feedback loop. So we measure that with the potentiometer, and then that goes back and goes through the analog to digital microprocessor and all that stuff back to the controller to create our correction. So if you talk about a control valve without a positioner, you could have a hysteresis deadband or lag, referred to here as HDL. They can range between 10 to 25% of the total valve movement. Generally, with larger and older valves, you're going to have a larger HDL. With a properly functioning control valve with a positioner, you can have that HDL reduced to about 0.5%. So we're talking 20 to 50 times improvement in the control performance. If we restated this, if we had a control valve that had an inherent HDL of 25%, we can control that flow rate at a 0.5% precision level by just adding a positioner. So control valves with low levels of friction can actually achieve a control rate that approaches 0.1% when a valve positioner is used. So now we're going to talk about Idp and pneumatic positioners. So I believe Rick.
Yep. So originally there were process controllers or stack controllers that were pneumatic, and plants that had these, if you've ever been in a control room, today you see multiple screens of HMIs and everything's digital. Well, back in the day, they were all pneumatic. So you would have a big panel with a whole bunch of single loop controllers, and there would be 3 to 15 PSI output. And then the controllers would either send, whatever kind of control signal to a valve. And in this case, you'll see on here the 4765 would receive that signal, and they would translate it into 3 to 15 PSI for the actuator and make the actuator move up and down. So today you don't see it that much, but where I've seen it is like in an air separation plant where you're supplying nitrogen to a client who has a tank farm, and they want to make sure they never lose their tank blanketing. So what they do is they have either a rack of these, or they have, well, you might be familiar with a Foxborough 43AP type standalone controller, and so then if they have a power failure, they never lose nitrogen. So that would be one application. There's a plant locally that we're now on some nitrogen valves finally switching to digital. And so Another application would be a remote area where you don't have power and you still you do have air or nitrogen, or even in oil field they use natural gas to power the actuator and the positioner, and you have a stack controller next to that that actually does the controlling on a level or a pressure or a flow. So drawbacks of that, of course, would be, especially over long distances, electronics is way better. You don't have the pressure loss that you would have in a pneumatic system. So on this valve, now you see an Idp converter. It just takes the digital signal and converts it to pressure. So that's basically the difference. So this is still old positioner technology, and this is actually very common with a separate Idp and a pneumatic positioner, and the Idp getting the signal from the DCS or whatever control system they have. So we do a lot of converting of these valves when people send these to us, and they, you know, in a data sheet, or we see it in the field and they want to convert, or they want a new valve. Commonly, we would change this to a pneumatic or a digital positioner with a built-in Idp. So I guess the next slide shows that. This is the 4765 that was on the previous slide. This is one of a few pneumatic type positions we have, or electropneumatic that we do have, and we also have a number of other ones. So this is just what we would call a dumb kind of electropneumatic positioner, and it doesn't have any auto tune or any other features, and you have to have a skilled technician to be able to calibrate these, and to but you still can take a pneumatic positioner 4765 and put this 6109 Idp module inside of there to convert it into a electropneumatic positioner. We don't sell a lot of these, but we do sell some. Typically, our customers want to go to smart, which would be the next thing.
Yeah. So this is an analog. So right here, you can see some screws and settings that you have to change to make modifications. So this is an analog. So the next slide, we're going to look at some digital and smart positioners. So in this group, we have three levels. So you have a basic level, which is going to typically just be 4 to 20 milliamp control. You know, you've got the 3725, which is in a plastic housing. So it's designed for non-hazardous environments. You then have kind of a general industry, general application, basic positioner, the -1 that offers 4 to 20 control. It also has the ability to do limit switches. You then have the next group, which is going to be your standard category of positioners. So here you're going to see full features and functionality that are found in all the similar state-of-the-art control valve positioners you find on the market. So you start off with just one that has all those features but no communications. That is a -2. If you want to add heart, that becomes a -3. If you want Profibus communication, that's a -4. If you want foundation field bus communication, that's a -5. We also offer it in explosion-proof enclosures. So here we change from the type 3731 to a type 3730 to a type 3731, and we offer that both in the heart and foundation field bus versions. The last category is our advanced positioners. So these are going to have enhanced features and functionality that are not commonly found in positioners, or they could actually be unique to a particular positioner that SAMSON offers. To better understand the advanced category, let's go ahead and look at our most advanced positioner, which is the Trovis 3793 in more detail. So this positioner has a few highlights to it. So the first is the fact that it has a protected non-contact travel sensor. So some of our competitors, they have a non-contact travel sensor, but it's external, it's not protected. We'll talk about the protected non-contact travel sensor in a little bit more detail later in this presentation. We also have a modular, flexible concept for the optional functionality and design of this positioner. I'll present that in a little bit more detail on the next slide. This positioner was designed around the existing 3730, so it has the same footprint and mounting parts that you would find in that 3730. We watched as a couple of our competitors struggled when they made the transition from contact to contactless with selling and promoting their positioners, as often the mounting kits, that attachment element would be something that would be lacking or missed in the changing over. So we tried to eliminate that by maintaining the same mounting kits, footprint, all that. The big design reason for the Trovis 3793 is the next point. So we made this inherently double acting. So this completely eliminates the need for a reversing amplifier that changes a device from single acting to double acting. We also introduced higher air capacities as process control valves are being demanded to be larger, to move faster, things like this. So this reduces the dependence on boosters and quick exhaust valves, and we increase that air capacity when you compare this to our 3730s by between 2 and 4 times of what we had prior. We also have plain text display, so it's very easy to interpret what's on the screen. And this has the latest in HART revision 7 for communications. So a little bit about the modular concept. So here you can see the two areas for the modular construction. So we have our optional modules. So this is the addition of things like software inductive or mechanical limit switches, binary inputs and outputs, analog position transmitters, force venting functions, things like that. Force venting function is also known as a solenoid valve. We also have pneumatic modules. So here you can have up to 2 pneumatic modules. So you could have a single acting, single output, double acting, single output, single acting, double output, double acting, double output, or a special version, which is in the next slide, which is called 2 independent outputs. So here, what you're doing is you're allowing for large movements to be controlled by your secondary output that goes through a volume booster to move the valve very quickly to achieve your desired set point. And then as you get closer, or as you require just small movements, we can go to direct acting, where we use our output Y1 of the positioner to move that valve. So you don't have the overshoot that you would often see with boosters.
Yes, and as far as applications, well, one thing that customers like is, of course, the ease of repair, because these modules can be taken out and replaced, whereas in our other positioners you can't do that. And you can also have multiple functions added to it, which you can't do on the 3730 series. The 2 times the double signal with the 0.8 CV helps us eliminate boosters on larger actuators, which is good on like anti-surge, compressor bypass type applications. And one of the unique things about this that Joseph did mention, there is a separate control of 2 air outlets. If you need fast movement, but you also need tight control, you can move the valve very quickly with one module and then have it programmed to, or with both modules, I should say, and have it programmed to just use the one module for tight control. One application we did was some large 10, 12-inch double offset Teflon line butterfly valves on a membrane system with chlorine. And we were able to control these huge butterfly valves to plus or minus 0.25% accuracy with 3.5-second stroke times, which is really unusual. The resolution of these positioners is phenomenal, and the people that saw it in the field that had never seen it said it was amazing. So it's an awesome advantage for us on some of these applications.
So continuing along with that new technology, we're currently here at SAMSON transitioning to our generation 2 of the 3730. So we're moving all of the 4 to 20 milliamp based digital smart devices, which would be your type 3730-1, -2, and -3 to the Trovis 3730-1 and Trovis 3730-3. The term Trovis just kind of helps delineate the fact that this is the generation 2 from the generation 1 model. So when we talk about the product highlights for these new positioners, here we're talking about that protected non-contact travel sensor like we saw in the Trovis 3793. We're talking about a significant reduction in air consumption. So we already had a relatively low air consumption in our 3725 and 3730 at 0.06 standard cubic feet per minute. These new Trovis 3730s have a 1/3 reduction, so we're looking at 0.04 standard cubic feet per minute for air consumption. We're using the same footprint mounting kit. It's really the same externals. It's the internals, the electronics that we've changed. In this new positioner, we can now offer 2 inductive limit contacts, whereas in the old one we could only offer 1. We also have that plain text display in the -3 for the Heart version. And then also in that -3, the Heart version, we're using the latest Heart revision, which is revision 7. So now here's just kind of an overview of now what the new product portfolio would look like. So we've removed that -2. So 85% of the prior cells that we saw with the -2 can easily be met with the -1. So we're moving from something that was used to be in that standard category more into our basic offering. So that helps.
So application-wise on all these, the basic positioners would be more geared towards indoor applications like food and beverage, pharmaceutical, things like that. The 3730-1 is very basic. It only has basically auto tune and a couple other functions. So people use these where they don't need all the other features and they're just less expensive. We sell these mostly on large projects, OEMs, things like that, where they don't need heart communication or diagnostics of any kind. So that's where we use those. It's also, you can get limit switches and 4 to 20 feedback with that, but we don't normally see a lot of that, the options being put in these. Probably we'll see more now that the 3730-2 is no longer going to be available. The next section, the 3730 3 through 5, These are the 3730-3 is our most commonly specified positioner because it's so easy to use and mount. The mounting and operation is really easy. It has diagnostics as standard, heart communication, Class 1 Division 2 FM approval, and a whole host of other options. We use this positioner probably about 90% of all applications. We have a very large inventory of those at every one of our locations, and it can be used on either linear or rotary valves. It's also the positioner we often sell to replace other people's positioners on other people's valves that we have designed and stocked kits, mounting kits for. So all that can be found on our website. One example of where we used a whole bunch of these because of their versatility and the options that they have is back in 2011, there was a chemical plant. We supplied over 50 on-off and linear control valves with these positioners for a SIL 2 upgrade. So this whole area was being reclassified as SIL 2 and hooked up to an SIS safety instrumented system control system. And these positioners had internal solenoid valves, internal inductive limit switches, and 4 to 20 milliamp position feedback for 1 out of 2 voting all in one device. So this is not typical in the US. It's more European or globally where you see that. But they were very happy with it. The standard partial stroke testing that it has as well allows them to check these valves quarterly with a partial stroke test and easily document that with our Trovis View software. And that is a standard feature for those. So those valves have operated very well. They've been overhauled as a PM, not because they were needed to, once since then, and those are still working quite well. The 3730-4 and 3730-5, the 4 is Profibus protocol, and the 5 is Fieldbus protocol. We don't sell a lot of these because not a lot of plants use Profibus or Fieldbus anymore. Fieldbus looked, I don't know, a number of years ago like it was going to be the big thing and everybody was going to go towards that, but it wasn't the case. It just had a lot of issues. So we do have those, but we don't sell a lot of them. And in all these cases, the 3731 is the same internals, but with an explosion-proof enclosure. We often run into specifications that call for explosion-proof. And we always, if it's Class 1 Division 2, we always question whether they mean explosion-proof or do they mean FM approved for Class 1 Division 2, B, C, and D. And many times we can save a lot of money for the customer by just going with our standard 3730-3, 4, or 5. So, and then the 3730-6 I didn't mention yet. That's more advanced. It has valve signature, but where you need valve signature and you don't need higher end diagnostics. So that's what that's for. There's a couple other things. It has a fixed clutch rather than a slip clutch, which is in the 3730-3. So if you have severe water hammer, this is a better choice for that. A couple of the unique things that this has is remote mount. It's a special order because it has a different output on the back or a feedback arm. But we use those remote mounts in applications where you have really high temperatures on the valve and you can't put the positioner there. So you remote mount the positioner somewhere else and you can have a cable with a feedback on the valve up to 50 feet away. That would be for, again, high temperature, but also high vibration. Another thing that we've started doing with this positioner is ultrasonic leak detection, which is a device that mounts on the Nomura rail on the yoke. And you get a baseline vibration in the positioner, and then it monitors that. And if you start to have a leak by, through the valve, it picks that up and gives you a notification of that. So you can check that the next time you're going to have a shutdown, a regular turnaround. And so you're not just guessing that it's leaking by. A lot of times plants are suspect that a valve is leaking by, but they don't know for sure. So this helps out with that.
All right. So let's talk about the local operation. So when you are configuring and working with the positioners, you have kind of two versions. You have the 3725, which has 3 capacitive keys and an LC display, or you have our other positioners, which have a multi-turn push button menu driven operation with an LCD. So it makes it very easy to do local configurations and things like that. Most common way to configure the positioner would be via the local operational interface. We have the ability to use like a field communicator. So this would be primarily for your heart and foundation field bus positioners. There's not as much of the field communicator drivers for Profibus versions. You can also configure the positioner through a PC. So here you could use SAMSON's Trovis View software. You could use some type of asset tool or a DCS system. But once again, the most common used method is the operational local interface. I've had people ask for field communicator files and you know how to set it up through the PC. But most of the time, once I show them how to do it through the local interface, they find that to be much easier. As far as the auto calibration, there are 4 different initialization modes. So there is the mode that's called NOM or nominal. So here we are going to find the fully closed position, and then we are going to stroke the valve, the rated travel that you've entered into the positioner. So for our standard 1-inch, 2-inch valve, that would be 0.6 inches or 15 millimeters. So it would find 0 and then move to 100% travel and record that as 0.6 inches or 15 millimeters of movement. You could also do max, where it finds both mechanical stops. So it finds the fully closed position, and then it finds the maximum open position. So wherever your greatest tolerance is. So if you have more movement in the valve or more movement in the actuator that's allowed, it'll find out where that max is, and you can achieve larger flows and have the full capacity of the valve. The third method of calibration is the manual. This is often used on rotary valves. For example, if you had a centric lined butterfly valve and you read the manufacturer's recommendations for setup, often they will say that you don't have to go to full 0 degree closed to achieve that tight seal. You can have a few degrees offset up to, I've seen like 10 degrees, where that resilient seated will achieve the 0 leak by, and yet you're not loading and creating a larger breakaway torque. So you could do that. You could also use it in applications where you need to maintain a minimum flow or make sure you don't go over a maximum flow. The last method of calibration is the substitution method. So this is when the positioner has become damaged, is no longer functioning properly. You can take that positioner off. You can put in a few parameters that kind of define what the positioner was on. So it's stroke, pin position, and you mechanically block the valve in a certain position where that is, and then you put the new positioner on, and rather than having to go through a full initialization, fully opening and closing the valve several times, the positioner will take all the inputs that you've told it and make a judgment on where it is, and then how much of a rotation does it have to achieve to go from that position to the desired control position, from fully closed to fully open. As Rick talked about earlier, we have simple attachment to a lot of common linear and rotary valves. We can mount our positioner in any position except for suspended, so we don't want the positioner hanging down. The positioner is independent of its fail-safe action or the moving direction, and the LC display can be rotated if needed to have the display read right side up if you mount the positioner what would be normally upside down.
Yeah, so just application-wise, the Fisher 657, 667, we have, I think, 3 or 4 different sizes. If Joseph can point out on there, I'm not presenting right now, but on the Fisher 667, we have a large plate that goes on. It's kind of unique, and you can see all the multiple holes in there. That's for all the different size actuators that they have. So it's really easy to install, and people like installing our positioner on those valves, on those actuators, even better than the ones that came with them. So we do a lot of those, as well as the rotary, which is right below that. And these kits were all developed for all these various sizes and shapes of actuators by a lot of them here in the US. And so we have drawings for those, and we stock these kits. So if somebody has a need for one in a hurry, we can usually accommodate that. A couple other applications that aren't on here that I wanted to mention. We've done piston actuators for air intakes, for dampers, big damper valves, also variable speed drives, which are not really control valves, but we have supplied our positioners and mounted them on VSDs where they needed better control. Worked out quite well. And one other thing, when Joseph was talking about initializing these or calibrating them on different nominal, max, whatever, whenever we do a valve that we don't manufacture, or if there's a rotary valve, we never know exactly where the stops are, we always calibrate on max, so that it starts at 0, closed, either closed or open, wherever the fail action is, and then goes all the way to full stop. So on those large green actuators, that's what we would do. We'd set the bench at 0 or 100%, whichever it is, and then we calibrate on max, and it gives you the entire stroke, which is usually much larger than a SAMSON valve would have.
So these positioners can handle various environments. So our standard enclosure is an IP66 or NEMA 4X. They can handle hazardous locations. So you have your non-incentive, Class 1, Division 2. You also have your intrinsically safe, which would be your Class 1, 2, and 3, Divisions 1, groups A through G, and then you have your explosion proof, which would be Class 1, typically Division 1, groups B through D. Ambient temperatures, so you can see the range of ambient temperatures that we can handle with the various positioner models. And then we also have what's called the air purging function for single acting actuators, where we can actually prevent corrosion by having the instrument air that is leaving the positioner be piped back into the actuator's spring side chamber, so that you're not pulling in atmospheric or plant air that could be corrosive in nature. These positioners are also SIL rated, as Rick talked about. So you have your SIL 2 and SIL 3 rating, depending on how you set up the system. So next we have the contactless protected travel sensor. So we have direct connection to the valve stem, so you can see that right here, and you can see that the actual non-contact part is internal to the positioner. So this measurement takes place inside the positioner. So this reduces the influences from interference, so your EMI. There's no adjustment of the sensors for different types of valves because our contactless sensor system is internal. You don't have to align the stuff on the actual valve. This also increases the durability due to less mechanical stress being placed on the valve, not having a physical linkage in the valve. The measuring principle used in our contactless sensor is an anisotropic magnetoresistive effect. So rather than looking at the magnetic field strength, we are using the direction of the magnetic field for our measurement. This concept is very similar to Hall effect sensors that are used in other non-contact positioners, but in general, the AMR sensors have a much higher sensitivity than the Hall effect sensor, and they can respond to both magnetic poles.
Yeah, so one application where I have a local chemical plant that had 3730-3s on all their valves of ours in 4 different units. And they found that the 3730-3 has a sliding clutch to prevent damage to the arm and to the internals of the positioner. And they decided because of that, they were having problems with the sliding clutch slipping and staying in position when they had a lot of water hammer. We weren't aware that they had so much water hammer in these units. So they just decided as a general rule to go to 3793 to replace any positioner that they had, and those are on any new valve that they buy, just because of that. But then they found out that it's very easy to use and it's very intuitive, and they really like it. Besides that, they also like the fact that they don't need boosters on a lot of the larger actuators, and that for double acting, they don't need reversing amplifiers anymore because of the 2 outputs on the 3793.
So now let's look at some of the integrated functionality that you can find in some of our positioners. So on these slides, you'll see on the right side where you can find that, whether it's a standard or optional feature. So when we talk about our limit switches, something that often comes up is the fact that these are a Nemours style. So with Nemours, we have 3 different states. So if you have 0 milliamps or non-connection shown, then that means that there is an open circuit or a line break. So you haven't made connection. If you're below the 1 milliamp output, then you have the non-conducting state. And if you're above the 2.2 milliamp output, then you're in the conducting state. So often that is in older systems, older DCS systems, that could be an issue, or where they're not able to differentiate between these three states, and they're expecting a connectivity, non-connectivity, those being the two states of the limit switch. For that, you would just need to get a switching amplifier that's based upon this, and if you needed help with defining one of those, you can reach out to us here at SAMSON and we can define what you would need.
Yeah, we don't have a lot of people that use the Nemura software switches, but I do have some, and it was a surprise to this one customer when they had a 3793, which doesn't have that as a standard, and we had to deal with that. But a lot of my customers are using these external limit switches. They like the bullet switches better, but we do have quite a few of these in the field. It works out really well. So it's easy to use. It's easy to set. It's modular. You can add it into an existing positioner. So that's another really good feature of that.
And on that note, I'll point to the fact that the last thing right here, you'll see these are two mechanical limit switches, which a lot of customers like. And also you'll see that there's no Nemura reference there. So this is what your customers would expect if they're looking for that connectivity, non-connectivity state. So we do have that if you want. Next we have the position pressure sensors. So these are built into the type 3730-6. You have two pressure sensors there. So this would be your supply pressure and your output pressure. And then in the Trovis 3793, because it's double acting, you'll have three pressure sensors. So you have your supply pressure measurement, you have your primary and secondary, or the movement closed, movement open pressure sensors. So there you have the additional two.
Yeah, so this was in the 3730-6 and the 3793, a great advantage for us to have a true valve signature. In the past, it was a calculated valve signature, and it didn't quite meet the needs of some of our customers who wanted to see the lower end and the higher end, the first 5% to see where the end position was, if it was changing over time, and also the upper end. But to be honest, most of our customers don't even use the diagnostics. They like to, they want to, but they don't. So we're trying to make a push for customers to actually use the diagnostics that's in these positioners. It's there, and it's recording from day one when they initialize the positioner. So we're just trying to get out there and educate people a little bit more about using the valve signature. You get a baseline, you record it, and then later when you're going to have a turnaround, you compare, you run a few tests and compare to the original, and you can save yourself a lot of money on pulling valves or leaving valves in that you don't need to pull.
So next we have our position transmitter. So this is a 2-wire system. You connect a power supply that is ranging in voltage from 10 to 30 volts DC. The internal component of the positioner will provide an output current 4 to 20 milliamps to represent the position of the valve, or it will send various other error indications or non-connected state on those wires for you as well.
So feedback of 4 to 20 milliamps for actual position. The most common thing is the place this is used is in SIL applications, SIL 2, SIL 3. where if you have an emergency shutdown, you send a signal to the positioner, you want to know for sure if it's moved, and if it doesn't come back saying it's moved to whatever the fail action is, then automatically your DCS cuts the power to the solenoid, either internal or external. So that's very common application. We used to sell a lot more of these for just indication without SIL, but now more people are getting used to using the heart signal for verification. So it's a mixed bag. We do sell these. It needs to be specified up front because it's an option. And one other thing is some people consider limit switches as feedback. When we hear feedback, position feedback, we always think of 4 to 20 milliamps. So we've started asking, do you mean feedback, analog feedback, or do you mean just a limit switch to show position? So.
And one note on that to add, Rick, on the 3793, because it's that modular design, if you failed to specify it, you can go back and correct that and add that later. So we can remember that fact. Next, we have the solenoid valve or forced venting function. Those are interchangeable terms. So here we I give an overview of how they function. You'll find that they're in general very identical. It's just what side of the Idp converter in that positioner block diagram that I showed. So in the forced venting function, we're going to prevent the current signal from reaching the Idp converter. And a solenoid valve, that's going to be a pneumatic device. So on that, it's going to be right after the Idp converter, and it's going to cut the air supply to the output. So there's a small difference. So if you look at the switching state of the forced venting function, it's slightly tighter with below 11 volts being the vent stage, and above 15 volts being the allow air to go through, versus 12 to 19 that you would find in the solenoid valve. There's also a little bit of a change in the static destructive limit. So you'll see with a solenoid valve, it's 40. And with the forced venting function, it's 38, but nothing substantial.
Yeah, and so with solenoid valves, the important thing is to know that it's there or not. Had a problem one time, somebody had sent out one of our valves to get repaired in an outside shop. They thought that the positioner was bad, so they changed it. They bought a positioner from us, but they didn't specify that it had an internal solenoid valve, and they couldn't get it to calibrate. And I went out to the field and looked at the label, and it didn't have the solenoid valve function marked on there. So you need to know they hooked up 24 volts to the two terminals for the solenoid valve, but it wasn't doing anything because it wasn't even there. But it's good that the positioner is smart enough to tell them if you know how to look at it. So like I mentioned, we don't sell a lot of internal solenoid valves because a lot of customers, especially for SIL applications, they want a separate device. They don't want to have a chance that if the positioner fails, then the solenoid valve also fails. And that's just an American thing. So.
We also have the external position sensor, so remote mount. As we discussed, this is used a lot for high temperature applications, vibration. And then I've also seen it used for placement of valves. So in hard to reach locations for the valve, they'll often move the positioner to another location.
Yeah, and you can also use these. Sometimes in the plant they have an Idp that's remote, and they have a pneumatic positioner on the valve. And it's just easier to mount the positioner where it's more accessible. So that's just ease of application. But yeah, the most common thing here is for high temperatures. We have a customer has ovens that the ambient temperature inside this building gets to about 145 degrees F. So you can imagine the steam valves, what the temperature is inside of those, and they were having problems with not the positioners failing so much as to the displays going. So they have moved every one of those to a remote.
We have a leakage sensor as well. So Rick talked about this earlier, where you have the little sensor right here that monitors vibration and noise, and it can detect if there is leak by when the valve is in its closed position. So you start off with a valve that you know is good, and you establish a baseline noise vibration level for the valve, and then as you know, once you put it into process and the valve wears, the amount of noise and vibration and things like that that would be created with the leak by that high velocity flow through the trim, the plug and seat, would be noticeable above your baseline measured value. Anything you want to add to that, Rick?
No, that's about it. It's relatively new, so at least to our customers. So we haven't really had that many applications in my customers, but you know, we're promoting it, and we just have to get to the point where they really have an interest and a need for it, or they see the value of it, I should say.
So next we have the built-in diagnostics. So as Rick said, the diagnostics are built into our control valve. So we have things like the data logger, which records information. This can be very useful. You could actually have the data logger start upon a failure event, and it would be constantly looking at the information. Once that failure event occurs, it will record. Then you can define this, say, 20 seconds prior, and then another 80 seconds after, so that we can see what was going on right before this failure event was identified, and then what happened after. We also have histograms for your stem position, so the travel of the valve or the set point deviation. We have a cycle counter, which establishes what we call the dynamic stress factor. So this helps identify where things like that. So when you talk about the travel diagnostics, this could help identify oversized valves or undersized valves. When you talk about the set point deviation diagnostics, here we can help identify tuning issues, signal issues. When we talk about the cycle counter, we can help identify frictional or set point precision issues. We also have the in position trending, so we can see if your valve trim set is eroding, if you have process buildup and process is hardening so that the valve can't fully close, or if you have some type of foreign object that could have gotten lodged in the valve. That would all be able to be noticed in the in position trending. We have our drive signal diagram Y, which is not based upon pressure sensors. And then we also have in the -6 and the 3793, the valve signaler, which is a pressure stroke curve. We have hysteresis tests, so this is going to be your change in friction. Once again, those are not going to be based upon pressures. And then you also have the valve signature friction, which would be based upon pressure measurements. You have your static characteristic or deadband detection test. We have partial stroke tests, a lot of times used for emergency shutdown devices, seal applications. We also have the full stroke test, and we have the optional leakage sensor, which we just talked about to help identify also leak by or wear to the internal trim. With that, we conclude our presentation, and I will open it up to any questions.